biological properties. It's also used in different food as additive, but also for non-food use, such as care products, bioplastic, and so on. But it is a problem for people who are affected by celiac disease or by gluten sensitivity. These people cannot eat gluten, so we have to develop gluten-free products. But it's quite difficult to produce similar texture of products without the presence of these gluten proteins. So in this talk, in this lecture, I will speak about rheology and structure of gluten. In the first part, I will define what is gluten, how you get it from the wheat flour, some biochemical aspect about the different protein that you can find in this matrix, a part where I will describe the rheological properties that were measured on this matrix in the linear and in the non-linear regime. Then I will speak about the critical gel model that is used to model this gel. And finally, I will speak about structure. What is gluten? Everybody knows gluten, but you do not necessarily know how to get it. It's quite easy. You take a flour. So in your flour, you have about 70% starch, 13% protein, 10% water. You mix it with water. You make a dough with about 50% water. This is a kind of structure that you can observe by electron microscopy. You can identify the starch granule and in between the gluten matrix. As starch granules are water soluble, you can wash your dough, you remove the starch granule, and you get the gluten. And if you look the structure by microscopy, electronic microscopy, you can watch this matrix and the presence of some remaining starch granules. So in gluten, you have half water, half dry matter. This dry matter is qualified as vital gluten that contain about 70-80% proteins, some residual starch between 3 and 20%, depending how you washed your dough, and some lipids. In food science, people used to use Osborne classification to separate the different kind of proteins, as Hadley introduced the first day. They look in which solvent you can solubilize your protein. So in wheat protein, there are two main families of proteins, the gluten protein, which are non-soluble in water, and these other proteins, which are soluble in water, that include albumin and globulin. But I won't speak about this protein because they are not in large quantities in wheat grains, and I will focus on this gluten protein. And in this gluten protein, there are two main families, gliadin, which are soluble in ethanol water, and glutenin, which can be solubilized in dilute acid or alkali solution because you introduce charge in your proteins, and it makes it soluble. But glutenin, a part of glutenin, can be also solubilized in ethanol water, and this is something that we use to get samples. So you don't have only two proteins in gluten. You have many, many proteins. If you reduce protein in a denaturing agent, you perform two-dimensional chromatography. You can separate your protein according to the molar mass and according to the isoelectric point. And you can define more than 60 spots, which indicate that we have more than 60 polypeptides in the gluten. A classical way to characterize a gluten sample is to use size exclusion chromatography using denaturing buffer, but without the reducing condition in order to maintain the disulfide bond that we can have between proteins or inside the proteins. And we can identify the two main families, the gliadin and the glutenin one. The gliadin which is ethanol water soluble, contains monomeric protein that may have intermolecular disulfide bond only, and the glutenin that can form intermolecular disulfide bonds. The molecular weight of gliadin is comprised between 20,000 grams per mole and 80,000 grams per mole. There are different kinds of gliadins. And in the glutenin family, we have a very wide range of molecular weight from 80,000 grams per mole until more than 1 million grams per mole. And if we look more carefully the polypeptide that we have in gluten, so here you recognize the gliadin family, where you have monomeric polypeptide chain, which either do not contain cysteine, so they cannot form intermolecular disulfide bond, or form intramolecular disulfide bond, thanks to an even number of cysteine. And the second family, the glutenin, which contains cysteine that can be involved in intermolecular disulfide bonds. And making polymers with these different polypeptides, we form such kind of linear polymers of glutenin polypeptides. An important point to say is that this protein contain a low content of charged proteins. That's why they are not soluble in water. And they also contain a large quantity of proline and glutamine that appear in repetitive sequence that are represented here in blue. And these amino acids are specific in the fact that glutamine can form hydrogen bonds and proline induce a disorder in the polypeptidic sequence. And as a consequence, this protein cannot be crystallized. They form intrinsically disordered proteins. You cannot get their structure experimentally, and that's why we only have modelization of the structure of this protein with this part which represent disordered part of the sequence. Now, if we compare this protein to the other food protein, so here I ask Adeline her plot, where she represented protein as a function of the rigidity and the hydrophoby. You can recognize here the main animal proteins, ovalbumin, lactoglobulin, and so on, which are very rigid and hydrophobic. Here you can see casein, which are more flexible than all these other animal proteins. Here you have most of the plant protein, plant globulin, and you find the wheat protein. Here you have gliadin, a little bit more flexible than globulin, and glutenin, which are specifically highly flexible and hydrophilic. And I will show you now that this specific sequence of protein induce specific rheological response. So in this second part, I will focus on rheological measurements that were performed in gluten, and I will see later how it was modeled. So people were interested by gluten because it has a large importance in the bread making process. The bread making process can be divided in five steps. First, there's a mixing step of the flour with the water, the fermentation step, the shaping, the proofing, with the creation of gas bubble and the increase of the size of this bubble, and finally the baking. To probe the quality of different flour, industrial people created machine to probe the quality of dough for the different steps, mixing, shaping, and baking. So typically, a mixograph mix the dough, and you measure the torque required to mix your dough. And this is a typical measurement that you can get. And bakers know very well that the optimum mixing time is defined by the maximum of the torque that you measure here. They created the extensograph. It's typically extensional rheology. And the alveograph that was introduced the first day by Peter to look at the ability of the dough to resist to the rupture of the gas bubble. Typically, you prepare a plate of dough, you impose a flux of gas, there's a formation of the nice bubble, and you measure the pressure as a function of time. But if we want to get a physical picture of our system, we have to perform rheology. So we have to use shear flow with high shear rate if we want to understand what happened during mixing. For shaping, it appears more important to look at the extensional properties with higher strain rate between 10 and 1,000 second minus 1. And for the baking, during the growth of bubbles, we have to probe the biaxial extension properties in lubricated condition. And here the strain rates are very low. The pertinent strain rate are between 10 minus 4 and 10 minus 3 second minus 1. So let's start with the measurement. It's quite difficult. Gluten rheology is challenging. It's sticky. It's a chewing gum. It's a nightmare. Then you have a variability in terms of composition due to the biological source of your gluten, the extraction process, and so on. And rapidly, when you start measurement, you realize there's a mechanical history dependence of your measurement and an aging. Here's an example of the stress relaxation measurement that was performed at different aging time. And you see that the measurement at short time is the same, but the long time decay is different and evolve after different aging time. Nevertheless, people measured typical frequency sweep. So there's a lot of frequency sweep measurement of gluten in the literature. I give one, which compare the rheological response of gluten with the flour, dough, and starch. Typically, the flour dough is characterized by this power law signature with an exponent which is close to 0.2, 0.3. And for gluten, we have this kind of shape with a power law regime at high frequency here, but it depends on the measurement that you perform, the gluten that you have, and so on. But we can say that we have a power law regime in a limited range of frequency. To understand something, people try to change the composition of gluten. They either added gliadin or glutenin to a gluten that they extracted, and they measured the elasticity as a function of this ratio, and they found that the elastic modulus decreases as the gliadin-glutenin ratio increases. And it's related to an increase of the tangent delta value. So people concluded the elasticity of gluten is due to this glutenin, which are the polymeric chain, which are cross-linked by disulfide bonds. However, with the measurement that were performed with native gluten in water, you cannot change the volume fraction of protein that you have in your samples. Because these proteins are not soluble, you cannot dilute it, you have a phase separation. That's why we choose to work with another solvent, ethanol water, I told you that it's a good solvent for gliding, and that some glutenin can be as well solubilized in this solvent. And we could get a model gluten in ethanol water, for which we can change the volume fraction of protein in our sample and perform measurement at different concentration. And here we found that for sample at low concentration, we have a G second that is over G prime. We have a liquid behavior, and as we increase the concentration, we reach G prime, which is higher than G second at low frequency. There's a crossing of G prime and G second. So we start from a viscoelastic liquid, and we finish with a viscoelastic solid. And for a given concentration, if we measure the sample as a function of aging time, we observe such similar transition. Here we start from a power law regime, so I will describe it later, which is characteristic of a critical gel. And as you increase the aging time, the low frequency modulus increases. And we found that all data that we measured at different concentration, different aging time, could be plotted on two master curves. To plot this master curve, we used two shifting factors, an horizontal one and a vertical one. Here we have data that were measured at low concentration and weak aging time. And here we have data that are measured for the highest concentration and aging time. And we can identify here a power law regime at high frequency with a slope of, with a power law exponent of 0.8, which is the same exponent that we found if we plot the shifting factor B versus A. We found the same power law evolution. With this kind of master curve, we can define the frequency at the viscosity at low frequency and the elastic modulus at low frequency. So we can plot this viscosity as a function of aging time. We can see that for the highest concentration here, we have a divergence of this viscosity. And for the highest concentration, we start from viscoelastic solid, and the modulus increase toward a steady state value. I will qualify this two master curve as a pre-gel master curve and post-gel master curve, but I will come back to this aspect later. But I show you that we have an evolution with time and concentration. And in fact, we can suppose that many data that are measured for different systems can be plotted on this kind of master curve. So we could identify the possibility to plot such kind of curves. The previous study was performed with one gluten composition. Then we decided to change the composition of our sample. Here we changed the glutenin content from 52% to 62%. Here we worked in water to be close to food aspect. And we work on only one concentration. We only play with the aging time. And we could define three kinds of master curve for different composition. And you can see that in all this curve, we evidence this power law regime at high frequency, but that is characterized by different exponents, 0.5, 0.45, 0.37. We have a decrease of this power law regime. If we plot this power law exponent as a function of glutenin for our model sample, including data from the literature here in blue and in gray, we could define a decrease of this power law exponent. And if we compare this data with the native gluten, it appears a bit different. And I remember what said Gareth, processing is as important as composition. Maybe it's not only a question of composition that dictates the behavior of this gluten. So this was the linear regime. Now we go towards a nonlinear regime, performing strain sweeps. Here, again, the comparison between starch, flour dough, and gluten. And you can see that the extent of the linear regime of glutenin is extremely large compared to the dough or the starch. This is very characteristic of gluten. We can also perform creep measurement. Here, the creep test was performed for stress below 200 pascals, and above 200 pascal, we have the flowing of the behavior. So people concluded that gluten display a yield stress behavior. Here, you can see the evolution of viscosity as a function of creep test. And here, you can define the shear thinning behavior of this sample. However, we have to be careful because we know that our sample ages, and this kind of experiment lasts about 20 hours. So we know that we have an evolution of the sample during this kind of measurement. Anyway, we can qualify that gluten is thixotropic. It depends, the response depends on the time. Viscoplastic material, this is a term introduced by Gareth during his lecture. What about extensional rheology? People generally perform bidimensional compression and uniaxial extension. Here, again, the comparison between gluten and the flour dough. You can see that the gluten stress is higher than the flour dough for both tests, but that the difference between gluten and flour dough is higher when you perform a uniaxial extension, which can be understood if we consider that we have more orientational effect in gluten than in flour dough, because gluten has a polymeric structure, whereas flour dough includes a large quantity of starch particles. Yeah? So that's not my picture. I took this picture from Maria. She's no more here. And I think she presented this picture during a lecture as well. And they can follow the extension rate thanks to the image measured during the test.
Okay. I will go and ask about the purpose.
Yeah, yeah. And generally, people perform this kind of test to model what is happening when there's a growth of the bubble, there's a decrease of the thickness of the walls, and they want to know if the material is able to prevent an homogeneous extension of the film. If we consider here the thickness of the film with a thickness of H and locally a thinner thickness, we will prevent inhomogeneous extension if it's harder to compress this thinner thickness than the thicker one. This is the inequality that is defined here. And if you derive this inequality, you find that the biaxial strain derivative of the logarithm of the stress has to be higher than 2. And a similar inequality is defined in uniaxial extension. This is what is called the consider criterion. If we look at experimental measurement, stress versus biaxial strain here, you can observe an exponential increase of the stress, and that depends on the strain rate that you use. And the term that you have here is qualified as the strain hardening index. That corresponds to the strain derivative of the logarithm of the stress. And people measured this strain hardening exponent for flour dough and gluten dough. They found that this exponent is lower than 2 for flour dough, and increase to larger value, larger than 2 for the gluten dough, and concluded that gluten is extremely important to prevent the evolution of bubbles in the dough. Finally, to finish to describe the behavior of this gluten, if you make several pieces of gluten, you stick them together. They look like glue. That's why we qualify gluten as gluten. And you get a unique material. Another way to measure this self-healing behavior is to perform large amplitude oscillatory shear for a certain amount of time, and then probe the recovery of the initial properties using small angle oscillatory shear. And you see that after 15 minutes, we totally recovered the initial properties. So it's all descriptive, what I presented you for the moment. If we want to go further, I have to introduce a critical gel model that was previously introduced by Gareth, but I will add some things. This is not Gareth. This power law rheology is measured in different systems, many different systems. So the saltwater toffee, gluten, but also biologic material, asphalt, concrete, liquid crystal, gels, polymers. So you cannot define the structure of your sample from the fact that you have a power law rheology. Generally, you measure a power law evolution of G prime and G second as a function of frequency. And if G prime is over G second, this power law exponent is below than 0.5. If G second is over G prime, this power law evolution has an exponent higher than 0.5. And G prime equals G second when this exponent is 0.5. Equivalently, we can measure the stress relaxation. You can measure a power law decay of the relaxation modulus. And if you look at the relaxation spectrum, it's also characterized by the same power law decay, which indicate that we have a very broad distribution of time scale in a whole sample. So Gareth and his team performed many measurements on gluten, and they modeled their data using the critical gel model. So here are the data. You can see that at short time, we have a response that's not a power law that was attributed to a Rouse regime that I won't discuss here because it's not measured in all cases. And the power law regime that can be modeled by this equation that define a gel strength and a critical exponent. Using this equation, we can derive the response in dynamic frequency sweep. So here I look only this regime at low frequency, long time. And here is the equation of G prime as a function of the frequency that depends as a omega's exponent n, the same critical exponent. And tangent delta, G second over G prime, is expected to be related to this power law exponent. Equivalently, we can model creep measurement in the linear regime. In that case, we have the compliance that evolves as a power law as a function of time with the same critical exponent again. And you can see, and as long we are in the linear regime, we have this power law evolution of the compliance. More interestingly, they also succeed to model uniaxial extensional flow of gluten using this critical gel model. Here are the measurements. So the stress difference as a function of time for different strain rate. And if we look at the model in the linear regime, we expect a stress difference that depends on the strain rate with an exponent n, and that depends on the strain with an exponent 1 minus n. So plotting this data divided by the strain rate at an exponent with a power law exponent n, you get one master curve for all the different data in the linear regime, but also in the nonlinear regime. And in the large strain regime, they define a model that depends exponentially of the strain that fit also data at large strain. And they define an equation that models data on the whole range of strain thanks to this equation. So we show that Gareth showed that there was strain rate separability, and that's for critical gel model, the strain hardening exponent expected is 2. However, as I told you, we don't always have a critical gel regime in our measurement, depending on the time, on concentration. Sometimes we have something that flow at low frequency or that behave as a solid at high frequency. And this is a kind of behavior that we find in near critical gel. When you have a system that progressively gel, it can be made of particles or polymers. You form clusters with a wide distribution of size. And at some point of gelation, there's a percolation. You create an infinite aggregate in your sample, which corresponds to the critical gel. And above this point, the gelation will continue, and the mesh size of your gel will decrease. If we look at the relaxation time spectrum of this kind of system, it's expected that we have a power law distribution of relaxation time. In the critical gel, in which the largest cluster is infinite, this distribution of relaxation time goes towards infinite value. Whereas for the pre-gel, the longest relaxation time is associated to the largest cluster. So the relaxation time spectrum is truncated here at tau z, which represents the longest relaxation time in your sample. Equivalently, in the post-gel system, the relaxation spectrum is truncated. Given this relaxation time spectrum, we can define the dynamic frequency response. Here are the response of pre-gel that flow at low frequency, the critical gel model, and post-gel system, which are here. We can plot tangent delta as a function of frequency, and you can see that the pre-gel system is characterized by a decrease of tangent delta as a function of frequency. The post-gel is characterized by this increase of tangent delta, and the critical gel is recognized by the constant value of tangent delta. And this tangent delta value depends on the critical exponent n. And Muthukumar proposed that this critical exponent will be associated to the fractal dimension that we have in the sample. Even more interestingly, for some system, it was found that this dynamic frequency sweep curve could be plotted on two master curves with the power law regime here and with a relationship between the shifting factor that are used here, tau z, and 1 over GE here. And this is exactly what we measured for gluten. The fact that we can plot this kind of master curve indicates that we have a self-similarity in terms of structure of our samples. Another way to model the data is to use elementary component spring, dashpot, make Maxwell. If you have a Maxwell model, you expect an exponential decay of the stress as a function of time. And if you want to model a power law decay, you need several exponential decay, and you have to use a generalized Maxwell model for which you expect a sum of exponential decays. However, using this, you need many characteristic time to fit your data. That's why another viscoelastic element also introduced previously was created. This is a spring pot. That is an intermediate between the spring and the dashpot. The spring is relates the stress versus the strain linearly, whereas the dashpot relates the stress to the strain rate linearly. So here is the first derivative of the strain. This is the time derivative of the strain. And the spring pot is intermediate. The response of the spring pot is associated to a time derivative of the strain, and with the order of the derivation that is not that is a fraction. And there's a prefactor here that is qualified as quasi-property because the dimension of this prefactor is quite strange. Anyway, if the order of the derivation here is 0, you get a spring. If the order of derivation is 1, you have the dashpot, and all intermediate value between 0 and 1 can be used. And using the fractional derivative operator, you expect for a stress relaxation of a spring pot a power law decay of the relaxation modulus as a function of time, with the exponent here, which correspond to the derivative order of the spring pot. Equivalently, for the frequency sweep, you expect power law dependence on the frequency. So this is a good tool to using a one spring pot, you can model a critical gel. And if you want to model pre-gel or post-gel, you have to combine spring pot with dashpot and springs to make a fractional Maxwell if you want to model a pre-gel, and a fractional Kelvin void if you want to fit post-gel data. This is what was performed by the team of Thibaut for a totally different system, cellulose and a crystal suspension. We could do exactly the same fitting, but it's not done for the moment. So, the last part. I don't want to be a theologist, so I will speak about structure. In food papers, when people speak about gluten network, generally they speak about the distribution of gluten in dough. Here, there are proteins which are labeled in black, and they follow the evolution of the distribution of this protein in the dough during the mixing time. And they observe that at the maximum torque, there's a percolation of this protein phase. And they also look the different kind of gluten protein in this matrix. And they look at, briefly they found that there's a colocalization of the different kind of protein. There's no separation in the different kind of protein. And if they submit their sample to large strain amplitudes, they destroy the network of gluten in their sample. But it is the structure of the gluten at large scale. If we look at smaller scale, different models were proposed in the literature. First, in Nature, Wigley proposed that gluten was an entangled polymer network. This model was proposed on the fact that gluten is elastic, it displays high extensibility, as I shown you previously, and we have very large polymers of glutenin. So they considered that we have a network of glutenin cross-linked by disulfide bonds, and gliadin would act as a plasticizer in the network. However, in parallel, Wellner and Belton proposed another model because they wanted to model the fact that there's a reorganization of the network under mixing, and they also observe an evolution of secondary structure during compression test. And their proposition was that we have gluten protein cross-linked by disulfide bond. As we shear, there's an orientation of chains of gluten protein that induce the formation of intermolecular hydrogen or hydrophobic bonds. And using higher mixing rate, we would break disulfide bonds. So in that case, people consider that gluten is a transient polymeric gel. And the third school, the hyperaggregation model. In that case, they said we have a sample that displays a power law analogy, yield stress, aging. At the same time, there was a SGR model that was introduced yesterday, and they said, oh, it's similar to what is observed in a dense particle system. So maybe we have a particulate gel model. So they look at their sample, and they found that using a surfactant, 1.5% surfactant solution, they could get insoluble parts that form a particle with a size comprised between 1 and 10 micrometers that they qualified as glutenin macropolymers. So they said the rheology is dictated by these objects that could percolate at larger scale depending on the mechanical history of the sample. So, what is the structure of gluten? It's difficult to get the structure of gluten because it's not soluble in water. Typically, people perform rheology in water to mimic the gluten that is extracted from dough. However, if they want to fractionate the different proteins, they have to solubilize it, to dilute it, to obtain the different monomers and polymers. They do here size exclusion chromatography using surfactant and urea. And if they want to get information about polypeptidic chain, they have to add reducing condition. So all structural studies at that time were performed in the dilute regime using surfactant, from which we can expect the formation of complex between protein and surfactant, which is not really relevant compared to the gluten in water. So our point was to use the water ethanol solvent I introduced previously, in which proteins are partially soluble, but from which we can get both gliadin and glutenin and get composition similar to the native gluten, and which is less chaotropic than this kind of solvent, and from which we can perform as well rheology on dense sample. We are in soft matter lab, so what we do, we perform SACs. We perform SACs on gluten sample prepared in water and in ethanol water. What we observe on this SAC signature is a typical SAC spectra that you can obtain for a polymeric gel. There are different features. First, in the high Q regime here, there's a change of slope that can be attributed to the persistence length of the polymers. We get it here we got it a persistence length that is typical for disordered proteins. Then there's a power law regime here that is attributed to the change statistics. You can see that the slope is different for the two solvents, and as expected, for ethanol water, which is a better solvent than water, we have a weaker slope, 1.5 compared to 2 in water. So here I refer to the lecture of Peter that introduced the change statistic of polymers. If we go at larger scale, at lower Q, here we have the signature of blobs. And at even smaller scale, here we have the signature. We have a power law evolution that is associated to the fractal dimension that we have at larger scale. An interesting point here is that the slope at small q is very different if we consider the model gluten and the native gluten. The difference between these two samples is the content in insoluble glutenin. We increase the fractal dimension, we increase the density of the network if we keep this large insoluble glutenin in our sample. We also have often sans beamline in the lab. So we decided to measure our sample as well. In sans, if you want to have a large contrast between your protein and your solvent, you have to use a deuterated solvent with your protonated proteins. So we prepared sample in a deuterated solvent. What we see here, in orange here, we have the SACS data I presented previously as described. And here is the data that we measured for the sample measures in sans. And it was really not expected if we consider that the solvent is deuterated and the protein are hydrogenated. The sans spectra is characterized by a Q-4 slope here that's defined sharp interfaces and a characteristic size here of about 60 nanometer. And if we increase the glutenin content in our sample, we see that the intensity of the signal increases. So it's also associated to these glutenins. Based on this data, we can consider that in SACS, we have a contrast between the contrast is due to the electronic density difference that we have in the protein and the solvent. We have a contrast between protein chains and the solvent. We have this kind of polymeric gel structure. And in sans, we define here a large scale object that is due to difference of contrasts that we have in our system that define object with a size of 60 nanometer. And we can understand this if we consider that when you mix an hydrogenated protein in a deuterated solvent, there will be an exchange between deuterium of the solvent and hydrogen of some residue. You can have a deuteration of your protein that will not be total. It will depend on the accessibility of protons. And using contrast variation that I won't describe here, we could define that we had a limited exchange of protons and deuterium in our proteins, an exchange evaluated at 57%, which is much smaller than the typical value that are expected for a classical protein that are well soluble in their solvent. So we showed here that we have an homogeneous repartition of deuterium at the microscopy scale that evidence large-scale heterogeneities of interaction of our sample that will be associated to this glutenin. But what are the interactions that govern the gelation of this sample? The first answer can be given by the fact that you can solubilize your gel in urea. It means that we have the gel are governed by physical interactions. That's not the disulfide bond that maintains the gel. This is it refutes the first model of Ringley. Another interesting experiment is here, the swelling experiment. We start with a gluten gel, and we let it swell in its solvent, and we measure what is released by the gel and how the composition of the gel evolves with swelling. We can see that as the gel swells, we are enriched in glutenin, and if we probe here the proteins that are released, we measure a constant profile as a function of time, which is not expected if we consider that gliadin and glutenin are independent, because their size are very different, and we would expect a faster release of gliadin than glutenin if they would be independent. Here we show that we have a co-release of gliadin and glutenin, suggesting an interaction between these two kinds of proteins. So the question was, what are the building blocks of this gel? And to get the building block, we have to dilute it to separate the object. We cannot do this in water, it's insoluble. We did it in ethanol water, and the tool that we found to separate these building blocks was asymmetric flow-feed flow fractionation. These techniques enable to separate objects according to their radius of hydration, from nanometer size to micrometer size. The principle is to use a channel that is characterized by a frit on the bottom side and a membrane, which enable a flow of solvent in the perpendicular direction. So we used two flows, a tangential one and a perpendicular one. The tangential one is used to confine the sample laterally and then to elute the sample, and the perpendicular one is used in the focus step first to confine the sample close to the membrane. And during this focus step, there are both the objects that are confined to the membranes, but also Brownian diffusion that induce a larger displacement of smaller species, and that will be eluted at larger speed than species that stay close to the membrane due to their larger size. That's why when we elute, the first species we eluted first, and the larger species will be eluted later. So we developed a method to separate our proteins in water and ethanol. It's not so easy because water and ethanol is very viscous, 2 times water, roughly. We succeed, and we could fractionate different model samples with different glutenin content. We identified that at short elution time, we get monomeric species with a molar mass consistent with monomers. Then we have species with a molar mass consistent with polymers. And at longer time, we define proteins that are eluted with a radius of hydration, which is about 80 nanometers. We find again the typical size that we found in SANS. And if we look the repartition of the different families as a function of glutenin content, we can see as we increase the glutenin content, we increase the content in assemblies and polymers. So the question was, what are these objects, these assemblies? Are they important as building block of our gels? A way to characterize this object is using light scattering techniques, static light scattering and dynamic light scattering. By static light scattering, you get the radius of gyration, the molecular weight. You can define the internal concentration of the objects, the Rg over Rh ratio, which gives us a value that is typical of cross-linked polymers. Here we perform the dynamic light scattering at different scattering angle, and we plot here the decay rate as a function of the scattering angle. And we can define here 2 regimes. A first regime that is evolved as a function of Q2, which is a diffusive regime, from which we can extract the radius of hydration as you do classically in dynamic light scattering. But at larger Q, we can define a second regime with a Q-powered free evolution that is associated to an internal dynamics of our object. This is the dynamics of polymers inside these assemblies. And here I refer again to the Peter lectures and as well the Laurence lecture that explain this power law evolution. So we have floppy objects, and if we look at the composition of this object, they contain both glutenin and gliadin. So it's not only glutenin that build these assemblies. Another last interesting point was observed when we tried to inject different quantities of our sample in the asymmetric flow field fractionation. We found that the repartition of the different species was different as we increase the quantity of protein injected. So you see that the assemblies increase as we increase the quantity of protein injected. And if you remember the principle of the technique, there's this focusing step at the beginning of fractionation, during which we form a very high concentration of protein at the bottom of the channel that could induce the formation of assemblies during this step. But interestingly, we found that if we collect this assembly and we re-inject only these assemblies, proteins are eluted at short time, which indicates that we have an equilibrium. The reverse is also possible. It's a kind of micellization of these proteins. I don't know. This is the end. This is where we are. To conclude, I've shown you that gluten is a complex material, but we can learn things from an analysis using soft matter tools and theories. We learn things using conditions which are really different from the application condition. We used a different solvent, a very wide range of concentration, which was not done by the previous studies. The rheological properties of gluten are characterized by the power law rheology, the thixotropic behavior, a high extensibility, strain hardening, which are well described by the near critical gel models. This gel is made of disordered protein, which are interaction through covalent dissolved bond, but more importantly by non-covalent bonds, which makes this protein very sticky, and form dynamic mesoscopic objects that contain both kinds of protein, which would confer transient features to these polymeric gels. So the image that we have from gluten presently is the following. Polymeric gel of protein cross-linked by some disulfide bonds, but more importantly, the hydrogen, maybe hydrophobic bonds as well, and characterized by this heterogeneity of interaction that makes an heterogeneity in the sample that could be important in the behavior of the sample that could confer maybe jammed system features. The question, the open question relative to the topic are associated to the transient properties. What are the bond lifetimes, the network dynamics? How does this network reorganize under shear, fatigue? How does it recover the initial properties? And the final question from this fundamental knowledge, how can we use it if we want to make gluten-free gels made with other sources of proteins? I would like to thank my collaborators and you for your attention.